All right. So, in the previous lesson, we talked about transverse and longitudinal waves. So, these are just representations of them, where in a transverse wave, the medium moves perpendicularly to the direction of the wave, and in a longitudinal wave, the medium moves parallel to the direction of the wave. So we're going to talk about sound waves. The subject of waves is actually my favorite topic as far as physics is concerned. Um, and so because of the application, so we can talk about sound waves, we can talk about light waves, and we see and hear those every day. And so there are a lot of interesting things that happen as a result of the physics involved. So let's describe sound waves. What do I say? Regions of high and low pressure, air molecules vibrate but don't really change location. So when we have the physics teacher talking, blah, 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 and then the student listening, this is the student, they're really enjoying themselves in class. Okay, the air molecule, so there's a little air molecule. The air molecule doesn't go from my mouth to your ear, okay? What happens is that this air molecule vibrates a little tiny bit, and then this air molecule vibrates a little tiny bit. So this one bounces into this one, and this one bounces into this one, and this one bounces into this one, and they're bouncing, bouncing, bouncing. And then there's some air molecules right by your eardrum, and they are bouncing back and forth, and they move your eardrum, and that triggers your brain to say, aha, a teacher's talking. And yeah, that's the way it works. So let's take a look at this. So we're talking about sound waves, and sound waves, well, I'll let you figure it out. Let's see what happens here. Hey. Okay. So take a look at the X. There's some X's here, and those X's are just to represent a specific molecule. So if we were to follow this guy around, this air molecule is just doing this. It's not going from the speaker in this direction, but we definitely see, this is a speaker here, bumping those beats, and the sound wave is dispersing or traveling in that direction. So we could be over here listening, and we would hear sound, and it's not like the air molecules move out towards us. They move back and forth. Here we see a region of high pressure. Notice how the air molecules are all bunched up, and then here a region of low pressure, high pressure. Let's see if we can watch that again. Let's see. Oh, cool. Here we go. So regions of high pressure sort of move out, right? And if you follow an individual molecule, you see that it just kind of moves back and forth, and it's not exactly in a line. It's more of this circular motion. And technically, when we talk about ocean waves, it's not like the water molecules move straight up and down. They do move in this circular path. Sometimes those are referred to as surface waves. So there's a little bit of longitudinal motion and a little bit of transverse if they're going in this circular path. But whatever, we talk about sound waves as longitudinal waves because the air molecules move back and forth. That is what causes the region of high pressure to move, to propagate. I'm going to write that word. That's a good one. Propagate. Almost as cool as tangential. So when we talk about waves moving, we talk about them propagating. All right. Oh, there's our physics teacher again. Okay. And the students listening closely. This is like one of those old school, before hearing aids. The old folks would have this big, like, reverse megaphone they'd stick in their ear. All right. So let's talk about the energy transported by sound waves. Waves are going to transport energy without transporting matter, right? So the physics teacher is talking blah, 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 and the air molecules are not actually moving in this direction. They are vibrating, but sound energy is definitely transferred. So we could say sound wave propagates from the speaker to the listener. The way it works is that energy is proportional to, this little alpha sign, proportional to the square of the amplitude. So we'll write that. This is energy, so we can measure that in joules, and this is proportional to the square of the amplitude. So we'll see some examples of that in our bookwork, proportional to the square of the amplitude. So like, here's equilibrium, and if we were to draw a wave with twice the amplitude, okay, so we could say that the red wave has about 4 times the energy of the blue wave because it has about twice the amplitude, right? Square 2, we get 4. Alright, so we got the energy is proportional to the square of the amplitude. And when we talk about sound intensity, alright, you may have heard of the decibel scale. That's a little weird. I'll show that to you in a bit. Okay, so when we're talking about the intensity of sound, we're talking about, so if we were to measure the area of this circle, we actually call that the cross-sectional area, and that's kind of because if the sound waves are coming this way, and this is some area that's perpendicular to the direction of travel of the waves, so it's going to pick up sound waves within this area. So we can talk about the power, right? Power is energy per time, divided by area, and that's what we mean when we're talking about the intensity of a sound wave. So you know there's a loud sound, or there's a soft sound. And so the loud sound has a high intensity and the soft sound has a low intensity. But what does that actually mean? We're talking about power. So, who knows? Well, yeah, we don't really have to get into the units of this. But, yeah, power per area. So this person could be listening and whatever. But you should at least be slightly familiar with the decibels. So this is a way of measuring the intensity of sound. And it's a logarithmic scale. We humans are pretty cool, and one of the ways in which we're pretty cool is that we can, our ears are incredibly sensitive. So we can listen to, it's like if we were looking at energy and sort of our perceived loudness, okay, we can hear really, really, really small amounts of energy, and then, or sound waves that have very, very little energy, and then we're actually able to, so this is going to be funny, and then, and then we can, for really long, and I could keep doing this, right, and it would go way off the scale, which it already did. Let's see, okay, this is totally messy now. Nice work, Torville. So anyway, nice, okay. Get out of there. So you get the picture, in that we have the ability to hear very low energy sound waves and to tolerate very high energy sound waves. And we just think of it as, oh, that's somebody whispering, and oh, whoa, I'm rocking out at the concert, okay? But, so if we actually assign numbers to these, we put it on a logarithmic scale. So when we talk about, let's see, painful acoustic trauma, right? Well, rock concert. All right, so a little bit less than that. So here we are jamming out, and it sounds pretty loud, but who cares, right? And then something just super soft, a watch ticking, or whispering in the library, leaves rustling is what sometimes is described here for really small, like 10 or 20 decibels. So our ears have the ability to perceive this, but also tolerate this. And this is not, when we talk about 20, this is not 6 times the amount of energy or energy intensity. And I don't know the number, we could calculate it, but it's a lot more. And so we put that on a logarithmic scale, and then the numbers are easier for us to deal with. Okay, so lastly, we can talk about the inverse square law, and we've definitely talked about the inverse square law as it refers to gravity. So we had the Earth, and so this is Earth, and we were talking about the gravitational force. So, at 1 Earth radius, gravitational force is something, you know, our weight, or we could talk about 9.8, the acceleration due to gravity. And if we double the radius, the gravitational force decreases by a factor of 4. And if we triple our distance, the gravitational force decreases by a factor of 9. So this is inverse square law. And the intensity of sound happens similarly, because if you think about, here's blah, 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 right? These sound waves don't just go forward. If I were using a megaphone, it kind of does, because it helps direct the sound waves. But when I just talk, they actually spread out in these spheres, okay? If I were to turn my back to you and still talk, you could still hear it. And because it's the sphere, and we're talking about the area of the surface of the sphere, it behaves like this inverse square law. So if I were 1 meter away and the sound of my voice had an intensity of 1, and we're just making up some units here, it would be like that. Actually, let's forget about it. We just talked about decibels. So if I were just sort of talking, maybe that would be, let's see, conversation. That sounds good. I'm not very loud. We'll go 60 decibels. All right, 1 meter away from Torville, and a decibel, an intensity of 60 decibels. And so if you were twice as far away, the intensity would decrease by a factor of 4. So we'd be at 15. And if you're like, I can still hear him, I'd rather not, you can move to a distance of 3, and then it would be 1/9 the intensity. And so 60 divided by 9, which is something, you know, like 6 point, I forget. Or, well, yeah. And then if you were like, what, Sonny? I can't hear you. And you're going to move in close, all right? So relative to 1 meter, you have halved the distance, right? And so the intensity would go up by a factor of 4. And all of a sudden, that doesn't sound realistic. 240 decibels. That would be loud acoustic trauma. So, I'm going to put a little question mark, because this is not a very realistic example. But that said, sound waves do behave like the inverse square law. Okay, and lastly, so we talked about waves reflecting off a boundary in the previous lesson, and I wanted to show you this. So with the waves reflecting off the boundary, what am I looking for? This, get this out of here. All right, so it was a string, and the waves were going this way, and it was a fixed end. It would bounce off in a certain way, right? The upright wave would be inverted, and if it was a free to move end, then the upright wave would be upright, and so on and so forth. So when we talk about light waves, there's something cool that happens. So this is a soap bubble, and the soap bubble, one, we can see kind of this reflection of the sky, but we also see all these crazy colors in it. And we would see this because the soap bubble is thin. So there's this whole branch of science called thin films. And they end up being incredibly useful. If you buy an expensive camera lens, it's going to have this coating that's used to reduce glare. If you have some fancy sunglasses, they're going to have some coating on them as well. So the idea is, you see colors here, and this is color coded just so we know what this is. But the idea is that a light wave comes in, and some of it's going to bounce off, some of it's going to pass through. So this is the soap, all right, really zoomed in. And some of it's going to pass through, and some of what passes through is going to bounce off this. So this is going from soap to air. Yeah, some of it's still going to pass through. Some of it's going to reflect off and then come back out. And so from this light wave and this light wave, we end up getting sometimes what we call constructive interference. We'll talk about that. But I drew these waves in phase, meaning they're like teaming up. Hey, we have the crest here, and hey, we have the trough here. And because they're teaming up, we end up seeing that light wave more. And it turns out that different colors have different frequencies, different wavelengths. So for a certain thickness of soap film, we get constructive interference for a certain wavelength or certain color. So we would see different regions of color. We would see different regions of color because there are going to be different thicknesses in the soap film. So that's it for that. Thanks for listening.